I'm going to go live.
Okay.
Probably. Who can say? All right. I think we're live.
Press the button.
There's the gallery view. There's all of us.
Did I
Okay.
spell everything right?
So, everybody, let us know that we exist. Say hello to me so that I can say hello back to you. And also let us know how the audio levels are, because I had to mess with it pretty invasively on Monday when I did my show. So it might be the audio levels are a little messed up. So just let me know.
La la la.
Hello.
Hello,
Hey, you all sound
universe.
really quiet. You're all whispering.
Yeah. I'm not whispering.
Okay.
You're whispering.
No, certainly am not. All right. Hello to Aaron C., Astro B., Christian Woodland, David Dunn, David Fairweather, Frank Tippin, Giselle Sabrin, Jay Alex Anderson, Jim Ashby, John Musk, Johnny Zed, Julie Cartier, Nancy Graziano, Optimist Narkill, Paranor, Arinstro, Rich Wilson, Rick Schwartz, Sergusi, Tom Van Scotter, Von Lichtenbutts, and Zappin Zappin. Hey, everybody. Every week. Von Lichtenbutts. This is awesome. All right, so yeah, let me know how the audio is all leveled.
Yeah.
David Dunn says, "Hello, Mark. It's good to see you again."
Oh, hi, David. Yes, it's been a while.
Stop playing with things.
Neil Yu, Gina Rodkey, Mr. M.E. Smith, Sergio Botero,
See,
Ian Farquharson.
You said hi to people so
Farquhar.
early, and now you're going to have to do it over and over again.
I know. Uncle Bill Drew.
It's
People
true.
show up and they say hello. It's true. I should wait maybe. The problem is that I've learned that if you don't say hello within 5 minutes, then it drops all those participants off the list. So
Yes,
you've
that's
got
true.
5 minutes that whoever
They have
has
to
said
have done
hello to you
something.
within the last 5 minutes, they are considered participants. 0xyzabcx0. Hello.
You didn't even attempt to pronounce that as a word.
They're saying that the Slack channel's on the wrong channel. I don't think that's true. It might just not be live. There we go. Hold on. Let me make sure I'm jumped to the recent messages. Okay, there. There you go. Thank you, everybody. It's fixed.
Cool.
I think we're all good. Trap Squad. Trap Daily.
I love how there's
Nicole,
planets
Enoch,
hiding
Ray
underneath
Cornelius.
Kim's orchid.
Yeah. There's Pluto, who's not a planet. And there's
Dwarf
Sharon,
planet.
who's also not a planet.
No.
Well, okay, there's worlds hiding
There's
underneath your
worlds.
orchid.
Yes,
They are. They're taking shelter underneath the big leaves.
they're called celestial buddies.
That's been making the rounds again.
Love that.
Do we want to have a big argument about whether or not Pluto should be a planet?
No, we don't.
Never.
I have
Because we
one
all
of
know
the
the
rare-
answer.
I have a very rare answer to that question. I
Wow.
don't care.
I don't. That's my answer too.
That's also my answer, actually.
Yeah, perfect. Well, then I think we're all in
I
agreement.
care as much as Pluto does.
I want both Ceres and Pluto to have the same label.
Mm.
I think they're both dwarf planets, aren't they?
They are.
Fair
And as long as they're both the same, I'm good.
How about just a
okay.
binary planet?
Binary planet's good for Pluto. Doesn't work for Ceres.
No.
Yeah, but
no.
no, together. They're just
and the
all
Earth is a
together. They're
binary
one
planet.
binary planet.
The Earth is formally not a binary planet because
Well, I've seen people argue both directions. You're right. The center
I'm with
mass
Mark on
is
this.
within the Earth, but
Sorry, Pamela. I'm with Mark on this.
although when the moon was closer, it was a binary planet.
right,
Oh.
and that's why I've seen people argue both ways.
Because the Barry Center would have been outside the Earth
Yeah,
at that point.
yeah. Back when we had a significantly shorter day.
Also, when the moon, I'm not spoiler alerting, am I?
No.
Wait.
No, wait, no, it actually goes the other way. It will be a binary. We will be a binary planet as the moon goes outward. That's what I should have said.
Oh, really?
Yeah, it's where the Barry Center is relative to the
Yes.
surface of the body.
That makes sense.
So that means as it goes out, we will eventually be an Earth-Moon binary planet.
Oh, okay.
I know how
We're not-
gravity works.
We're not there yet, so that's something to strive for.
But I thought that when the moon is close, then its pull is a lot stronger, and the two will be whipping around.
Yeah, no, it's just the mass ratio and the distance ratio. It's really all it is. That's where the center of mass is. So as the moon goes further out, the center of mass between the Earth and the moon goes further away
And
from
our
the Earth's center.
rotation rate slows, and when it's closer in, we're rotating.
Yeah, it'll be a slower orbit, but it'll be a binary.
Huh. And then Earth will be locked to the moon. The moon will be locked to the
That
Earth.
I think never happens because the moon's too far away to ever slow down the Earth.
I've
And it's
heard
not gonna
like
get
it
any
happens
closer.
like in 50 billion years, long after
Yeah.
the sun has destroyed the Earth and the
But
moon.
I don't think
so-
we'll
the moon,
pretty much all
we
be dead
lose
by
the moon
then.
before then. I
Right,
think.
right. All right, we've hit our 5 minutes, so let's get cracking here. Let me put you all back into your separate boxes. There we go.
I don't want to be in a box.
Sorry. And here's me. Perfect.
Break out of the box.
That's what I do.
All right, we'll give you a chance to shine in a second. All right. Hello and welcome to the Weekly Space Hangout for Wednesday, May 1st, 2019. I'm Fraser Kane, publisher of Universe Today. This week, we are going to be talking about water on Itokawa, an icy scar on Titan. LIGO is living up to expectations, and the Hubble constant is still a great big problem for cosmology. Joining me this week, we've got on my screen Dr. Pamela Gay. Pamela.
Hello, everyone. How are you doing this week?
Thanks as always for being a semi-regular guest. Did you survive your hangout-a-thon?
It wasn't a hangout-a-thon. It
Sure.
was only one day. We did a 10-hour celebration of
That
the
is-
10 years of 365 days of astronomy, and it was easy peasy, and we went out for Korean food afterwards.
10 hours. That's a piece of cake. Yeah, these
It's
days.
nothing.
Yeah. We've also got Dr. Kimberly Cartier. Kimberly, welcome back.
Hey, Fraser, happy podcast day.
Yay, it's Happy Podcast Day, everyone. All right, before we get on to our special guest, I want to remind everyone, encourage everyone to take a moment and join up with the Weekly Space Hangout crew. Go to wshcrew.space. These are, of course, the fans, our executive producers. Once again, we have an incredible guest who I had nothing to do with. None of us did. The Weekly Space Hangout crew organized the whole thing, and here we go. We get to talk to him. So thanks to the crew, and you should really be a part of the crew if you are a fan of this show, especially in the dark times when we go through our hiatus starting in about 2 more months. So once again, wshcrew.space. All right, let's get on with the awesome interview. I mean, I'm assuming this is going to be great. Dr. Mark Showalter, welcome to the Weekly Space Hangout.
It's great to be here, Fraser. Thanks.
Now, we actually raved about your science, man, it feels like a couple of months ago, about something that you discovered. So before we get into that, who are you? What do you do?
Yeah, I'm a senior research scientist at the SETI Institute in Mountain View, California. And SETI Institute is, yes, that SETI Institute, although my research is fairly general planetary dynamics.
Right, so you cannot confirm or deny the discovery of aliens today.
Sorry, not. I'd have to kill you if I told you. But and no, I've never met Jodie Foster. Is the other question I get asked.
Right, of course. Yeah, you just pass all those questions along to Seth Shostak and then move on to discovering various small moons in the solar system.
That's right.
Now, so let's go backwards because you most recently made a wonderful discovery, and like I said, we raved about it here on the show. What did you find?
Yeah, so it's the seventh inner moon of Neptune. It's a little rock out there. It's called Hipaa Camp, and it's got a little strange place in the history of the Neptune system as a piece of the nearby moon Proteus, as near as we can tell.
How did you find this? And just to give people a sense of scale, like how small and how extreme is this object?
So it's about 16 kilometers, 10 miles or something like that. So it's quite small. It's actually so small that when Voyager had its flyby of Neptune in 1989, this body, if they had a bit better luck, they might have seen it. But in fact, none of the Voyager images happened to capture this little rock. So it was still sitting there all this time, and using the Hubble telescope, we were able to find it.
And I mean, you really use the Hubble Space Telescope. It took you several years to find it, right?
Yeah, it was. I've had the privilege to discover a couple of pieces of real estate in the solar system before, but this was by far the hardest because Hipaa Camp, as it's now called, is so small that you can't actually see it in a single exposure of the Hubble telescope, because if you expose too long, it just kind of smears out and you lose it because it's spread out across a bunch of pixels instead of just 1 or 2 pixels. So we actually had to come up with a whole technique in which we kind of stopped the moons from rotating. We sort of twisted all the images in a stack that lasted maybe 40 minutes that was made up of 8 5-minute exposures. And when you did all of that and then put them together again, you got essentially a 40-minute exposure out of 8 smeared out 5-minute exposures. And that's when this little guy turned up.
But that wasn't just in one set of exposures, right? You chased it over multiple years, right?
Yeah, so we had been observing Neptune in part to look for little moons and also to study the rings and other aspects of the inner Neptune system. We've been using the Hubble data, Hubble telescope, going back to I think our first observations were in 2009, and we've had a number of other observation opportunities over the years. It was really only when we had enough data in hand that we could kind of go back and do this analysis and realize that this really small object was there and had been there all along. It just, we had overlooked it.
And it is kind of, I mean, just how complicated, or like what's left? Is this like at the very limit of what you figure is possible? Or do you think that you can track down more objects of this size and smaller at greater distances?
Yeah, I think we're finished with the Neptune system in terms of what Hubble can do. Now, when the James Webb Telescope gets launched, eventually that will actually push the limits. If we look for moons of Neptune that way, we'll see could see something much smaller. I have a whole lot of Uranus data on the ground going back to I think 2003 in the case of Uranus, and some of that data. With this really intense computer processing that sort of untwists the motion of all the moons, it's possible we could find something else, but it's going to be tough. And I haven't seen anything yet in the Uranus data. I think, as I said, we're kind of done for Neptune.
Yeah, I remember Mike Brown, the destroyer of Pluto, was saying that it was really due to that next generation of really powerful telescopes. Once the big ground telescopes came online, it enabled a whole bunch of these new discoveries to get made. And then once the plane of the ecliptic had been fully explored, the discoveries started to drop away. And then it requires a whole new set of tools. And there are some pretty amazing tools coming down the pike. There's going to be these gigantic telescopes that are going to be coming online in Chile, as well as you say, James Webb. So maybe that will bring up a whole nother generation.
Yeah, I just wanted to note, many of the moons that we're talking about have never been seen from the ground, and Hubble, just by virtue of being above the atmosphere and a stable orbit where it can look for really, really long periods of time, and you don't have to worry about weather, it is way more sensitive for the kinds of surveys that we're doing. You really want to be space-based, not ground-based. And so even the next generation of ground-based telescopes probably won't be able to detect some of these moons, but JWST will. So that's kind of our next great hope for this kind of topic.
And so do you figure then you'll just continue the surveys that you've been doing and just take it to the next level? Because I know that like with all of the major planets, they all get a little Hubble time every year. I remember, like, there's a new release of the Hubble images of Neptune and Uranus almost every year as it gets close, right?
Yeah, so that's actually a team of scientists I know, and they're studying the atmospheres, mainly the atmospheres of the giant planets. And so they are actually not doing the kind of exposures, the really long sort of 5-minute kinds of exposures where you kind of blast away. The planet is a complete messed overexposure blur. But that's how you find these little moons. So the year-by-year stuff, it's either we do it or it doesn't get done because nobody else is really doing this kind of work.
But we can expect that when James Webb gets online, it should be doing the same kinds of surveys whenever these
Well,
planets are closest?
that's a matter of priorities, and we'll be proposing to use time on the telescope for this kind of work, but there's no guarantee we'll get it. We actually, I'll just note, we have. I'm on a part of a team that's got some Jupiter time in the first year on James Webb, and one of the things we'll be doing is studying this faint little dust ring of Jupiter and seeing if there's some embedded moons in there. So that's kind of the next opportunity I see for finding new real estate in the close vicinity of the giant planets.
And I mean, Uranus and Neptune, we've got to go back.
Oh gosh, yes.
Right? I mean, like the fact that you're making these kinds of discoveries halfway across the solar system is incredible, but also it's got to be a little frustrating because,
absolutely,
we need a close-up look to these incredible planets.
It's true, and NASA is looking at that. There's, it's going to be a number of years, and it's probably going to be scientists younger than me who get to have the fruits of that exploration. But because it takes a long time to get to the outer planets, even if you were to launch tomorrow. But NASA is realizing that Uranus and Neptune are kind of big holes in our knowledge of the solar system. And it's time to go back there with an orbiter, hopefully to both. If not, then at least maybe one of the two.
If you had to choose one?
That's so hard.
I know.
So I was actually part of a NASA study to decide how we might do missions to Uranus and Neptune. And we decided not to decide. We decided that you really couldn't, that there were good reasons to go to Uranus and there were good reasons to go to Neptune, and they're not really the same place. They don't look alike. They don't act alike. If you had to make a choice, Neptune has a slight advantage because of Triton, which is probably a captured body out of the Kuiper Belt, roughly the size of Pluto, in fact. And, because you get that along with the bargain if you go to Neptune, whereas you don't if you go to Uranus. That might give it the advantage. But really, Uranus is a fascinating place, very different from Neptune, and we really need to go to both.
So then, I mean, what are the big questions that you have today? I mean, you've discovered so many objects in the solar system. Has this given you more questions than answers? And what are the questions that you now would love to go and chase down?
Yeah, it's the way I look at each time you find a little object or a big object, of course, but you don't find them very often. Every time you find something like this, it's another piece of the story. I mean, the idea that Hipaa Camp was probably the result of a big comet impacting into Proteus early in the history of Neptune, and it's been there ever since. We never knew about it, but these moons these planets have been battered by comets over their long histories, and we now have a piece of that that we can see and maybe someday actually get some close-up images of. Every time you find something like this, there's a new piece of the story to be told. It's kind of like collecting butterflies. You don't really know what you're going to get, but every time you find a new butterfly, it's a different piece of the evolutionary history of butterflies. And in a similar way, we're just learning those pieces of information about these larger bodies.
And I think, when you look at like the close-up images of, say, Iapetus or Enceladus, the stuff that came back from Cassini, I mean, there are just so many interesting mysteries. How did they form? How did they get these structures? And of course, as you said, with Triton, there's the potential of cryovolcanism there. So
that's right.
All these.
Yeah, I mean, I actually remember going back to the Voyager days when we found this faint ring called the E-ring. Actually, it goes back earlier than that, but we imaged it with Voyager. This was back in 80 and 81 during the flybys of Voyager 2 and 1 at Saturn. And we saw this thing and we realized, that thing's got it's brightest near the orbit of Enceladus. I wonder what that's all about. And I actually had a paper I wrote in 1989 that said, maybe there are geysers or something like that on Enceladus, and that's giving rise to this thing.
Really?
So, I take a little piece, tiny bit of credit that, we were talking about geysers on Enceladus or something like geysers, for literally 1 or 2 decades before Cassini got there and said, oh, look, there are plumes. And it's like, okay. For some of us, it was like, oh, there it is, whereas everybody else was, blown away. This is amazing new discovery, but we had kind of suspected it all along.
So then what missions should people that you're working on, that people should be keeping an eye on to prepare for some new discoveries? I mean, obviously, again, you can't can't spoiler alert them all, but what should
Well,
we be looking
so
forward
it's
to?
I hate to say this, but there's going to be a little bit of a lull in outer solar system science going forward. So we've got the Cassini mission just ended. Juno mission is going on, but that's only got another year or so, I think. And New Horizons will continue sailing off into the Kuiper Belt, possibly having another flyby if we're lucky. But we don't really have any. But beyond that, there are no spacecraft even being built right now to go to the outer planets. So that means if we started a Neptune mission tomorrow, we'd still probably be well into the 2030s before we were in orbit around Neptune and doing that amazing science. So unfortunately, we've got to do remote observations for the time being, and things like Hubble's still going strong. It's an amazing instrument. I think it just hit its 29th birthday, something like that. And JWST coming online hopefully in the next year or so. There's going to be some new opportunities, and there are new capabilities of Earth-based telescopes, as you've noted. So we got some possibilities along those lines. But the amazing close-ups, we're not really going to see a lot of, at least for outer planets, right away.
Well, and now that we've had the second launch of the Falcon Heavy, all I see are deep space science missions. That's all I can imagine, is not communication satellites going to low Earth orbit, but deep space, fast-tracked spacecraft that can make their way out to, Uranus and Neptune quickly. 6 years. Boom.
Yeah, you want to go fast. That's how that was the secret of New Horizons, was launch a small spacecraft on a big rocket, and so it can cross the solar system in 9 years to Pluto. But for bigger spacecraft, you need the extra push.
Yeah. Well, Mark, thank you so much for joining us today. Where can people find out more if they want to sort of track your progress and be first to hear about the next moon that you've discovered?
I may be getting toward the end of that category, but www.seti.org is the website of the SETI Institute. You can find out about me, but more to the point, you can find out about, we've got 70 scientists, I think, doing all kinds of interdisciplinary research, all related to different aspects of life in the universe, and including SETI, literal SETI research using radio telescopes. So check us out there.
Wonderful. Well, thank you so much for joining us today. I really appreciate it. And if you do either discover aliens or find another moon, please let us know.
I'll definitely do that, Fraser.
Right.
Thanks a lot.
All right. Thanks a lot.
Bye, everybody.
All right. Let's move on to the space news portion of this week's show. Kimberly's on my screen. So, Kimberly, I choose you.
You choose me. All right. Well, let's set the Wayback Machine to 2005. When Japan's Hayabusa the First rendezvoused with the asteroid Itokawa out in the far reaches of the not-so-far solar system. Not really far at all. It attempted to collect a sample. It ended up getting about 1,500 grains of regolith from the surface of this asteroid and brought them back to Earth 5 years later. And now it's 2019, and scientists have, for the first time, done a chemical analysis on some of those grains to try and figure out how much water this asteroid actually has and what this water is made of. That second part sounds like it should be simple in that it's 2 hydrogens and an oxygen, but it's actually more complicated than that. And to jump to the ending there, the answers are this asteroid has a lot more water than we were expecting it to have for an asteroid of its kind. And the chemical signature of this water is almost identical to ocean water here on Earth and other material from carbonaceous chondrite meteorites that date back to the dawn of the solar system.
What does that mean, sorry, like to have water that is similar to the Earth's oceans? How do you know that?
So the thing about water is that you make it, H2O, but you can also make it using deuterium, which is hydrogen that has an extra neutron attached to it. And back when the solar system formed, the solar nebula had a very particular ratio of deuterium to hydrogen. And that ratio is reflected in the water that has hydrogen versus the water that is made of deuterium. And depending on where you were in the solar nebula, you incorporated a certain ratio of the regular water and the deuterium water. And if you compare two objects that have water and you look at their deuterium to hydrogen ratio, you can tell if they formed in the same place and through the same process. So the fact that an asteroid that formed in the inner part of the solar system, where things were dynamic and chaotic and hot, and most of this water should have evaporated, but it didn't, and it has the same ratio of deuterium to hydrogen as Earth's oceans, means that asteroids like Itokawa could have actually seeded a lot of water onto Earth back in the early times of the solar system.
So that's it. We know where the water came from.
Maybe. We have it's still a very open question of where the heck our water came from, because it's not just S-type asteroids like Itokawa that have similar chemical signatures, but some of the comets we've looked at have similar chemical signatures. Other types of asteroids do too. So maybe these types of asteroids contributed part of Earth's oceans, but probably not all of it. I would be very surprised if there was one type of object that gave Earth 100% of its water. But what it does say is that these kinds of asteroids, these S-type carbonaceous asteroids like Itokawa, could have actually given us maybe up to a half an ocean's worth of water, which is a lot more than we thought they could.
I have a soft spot in my heart for all of these missions that overcame incredible challenges to complete their mission. And I think, Kepler, how they were able to sort of partially rescue that spacecraft, and Itokawa the Hayabusa, the original Hayabusa mission, is really incredible what they were able to overcome to get that spacecraft to do its mission and get home.
I mean, it didn't do 100% of what it was supposed to do, but it did bring back the first in situ samples of an asteroid. There are 1,500 grains of the regolith that we got back.
Yeah.
There are very precious 1,500 grains of asteroid regolith. And we looked at 2 of them, and both of them say that there is probably a lot more water there than we thought.
David Dunn is asking, do we know about the oxygen 16 to oxygen 18 ratio?
I don't think that this particular study looked at the oxygen isotope ratio, but that is another thing they could look at if they wanted to. But they were particularly interested in just the deuterium to hydrogen because that is a direct proxy for water, where the oxygen could be a proxy for other types of molecules and not just water.
Like these tiny grains.
Yeah, these are like a few microns.
Yeah,
across.
They're so small.
They're so small.
Yeah.
And they were looking at not the whole grain itself, but tiny crystals within the grains, the pyroxene crystals, which are not even, 50% of what the grains are made of. So we're talking like fractions of a fraction of an asteroid surface.
Now, Hayabusa 2 has come back for revenge, has been bombing and dropping all kinds of spacecraft and harvesters and collectors, and it's going to come back with a lot more samples when it actually does return back to Earth.
Oh yeah. Hayabusa 2 is going to bring back so much stuff, crossing our fingers. OSIRIS-REx is also going to bring back a lot of material. Both of those asteroids are also carbonaceous asteroids, which are the ones that are the least altered by geophysical processes and solar wind and things like that. They're probably the closest to primordial rock as we're going to get. And so I think these scientists are hoping to actually analyze samples from both of those missions when they bring back samples in a couple of years.
And so then we'll get sort of 3 different places that we'll have these samples from, sort of different spots in the solar system.
Yeah,
and be able to
Bennu is pretty close to Earth, relatively speaking. Itokawa's a bit further away, and Ryugu's pretty far, comparatively far as well. It samples almost the entire range of space where these S-type asteroids exist. We haven't really gotten a lot of asteroid samples or observations even of these asteroids interior to the Earth's orbit, closer to Venus or Mercury. They do live there too. We haven't really, we're probably never going to get those, but we got the rest of the orbit.
Yeah, that's amazing. Pamela, let's talk about the crisis in cosmology.
Ooh, you're mute. You're
She's
muted.
But first, I would like to add on a little bit to what Kimberly was saying. With the OSIRIS-REx mission, we're actually going to be launching a citizen science project over on CosmoQuest so that you, all of you out there, yes, you out there, you can help us find the rock that OSIRIS-REx is going to bring back with what I can only describe as a very angry vacuum cleaner. So please, keep a listen, keep an eye out, because we are getting ready. We're hopefully only a few weeks away from doing this.
And we actually talked a couple of weeks ago about how sketchy all of the landing locations are on the asteroid, on Bennu, because there's a lot of much surprisingly bigger rocks around. So you got to find a sample that is not in a dangerous location on the asteroid. So this is going to be a challenge. Get to work, everybody.
I can't wait to be able to talk about this challenge, but when it comes to OSIRIS-REx, I can't wear my journalist hat, I'm afraid.
The moral of that story is they need your help.
Yes.
Go help them pick someplace.
Yeah.
Okay, so the real reason I am here this evening is to discuss cosmology in, I'm not going to say in crisis. It's not in crisis. No one's going to live or die. There might be a Nobel Prize again. But I don't think there's death involved. So let's go with kerfluffle.
the cosmology.
Not even the inevitable heat of the universe?
Well, that's still inevitable.
The big
that's
rip, the tearing apart at an atomic level, everything that matters, including matter.
Well, so Adam Rees is at it again. For those of you who haven't been following along with the story, back in 1998, Adam Rees was one of the authors of a pair of papers from a pair of different supernova research teams that demonstrated that our universe isn't just expanding, but that expansion rate is changing over time in a way that indicates there's something else going on. And we have given that something else going on the name dark energy. Now, this isn't to say it's necessarily a specific energy, a pressure, a particle. We have no idea what it is. What we know is there is, give or take, roughly 1 proton of energy per cubic meter of space throughout the universe. And this energy is exerting a pressure, or there is a pressure that contains this energy. I don't know how you want to word that. And it now appears that acceleration might have an acceleration, that the physics might be different, that we did something screwy. And the way that we got at this realization, and this is again thanks to Adam Rees's amazing observational astronomy work. He is one amazing observer. It was realized that one of the major sources of error in our understanding of the rate at which the universe is expanding is our ability to measure the distances to things that we're measuring the velocity of. If you're not entirely sure where they are, measuring how fast they're going gives you, well, an acceleration rate that has an error bar. And we want to get those errors as tiny as possible. And the errors in particular, in this case, are coming from one of the earliest rungs in how we, well, ring together all of these different distance measuring techniques. And this is the Cepheid variable star. These particular stars were first discovered in the early 1900s to have the same luminosity if they have the same period. This was the work done by Henrietta Leavitt at Harvard College Observatory. And ever since then, we've been trying to figure out exactly what the precise luminosity of a Cepheid is if it has a particular period. And there's errors that come in just from using different telescopes. So rather than using a bunch of different telescopes to measure a bunch of different stars, Rees was like, I'm on this. I'm going to do this with the Hubble. And one of the reasons this hadn't previously been done with the Hubble Space Telescope is when the Hubble locks in on an object, it takes a moment to lock in its guide star camera on a bright object so that it can very precisely track. Now, with these Cepheids, they don't necessarily want to track, because they're trying to get the light across multiple pixels, to look at the variations, to average out the noise, to do a whole bunch of really cool technical stuff. And they're really bright, so they don't need to expose for very long. So Adam Rees and his team, working in collaboration with folks at the Space Telescope Science Institute, figured out how to, well, not rewire, but reprogram the Hubble so that they use strictly the gyroscopes to jump from Cepheid to Cepheid to Cepheid within the Large Magellanic Cloud. And all the stars in that cloud are more or less the same distance from Earth. The same way I might say that from my seat here in Edwardsville, everyone living in New York City is about the same distance away. Heck, everyone living in Manhattan Island is the same distance away. So by using one telescope, by combining his results with things coming from Gaia and a whole bunch of other ways that got him to the distance of the Large Magellanic Clouds, he beat down the noise and beat it down and beat it down until he was able to say very precisely that the local, using Cepheids and supernova in our modern universe expansion rate, is about 74 kilometers per second per megaparsec of space. And that's awesome. This is like completely consistent with earlier results. It just has much smaller error bars. Now, the problem is that while it's consistent with earlier results, it's not consistent with all the earlier results. It's only consistent with other results regarding our modern universe. If we instead try to measure the expansion rate using techniques that involve what was going on in the first days of our universe, if we look at the baryonic acoustic oscillations, this is if we look at the sound waves that cause the different temperature variations in the cosmic microwave background, if we look at the dark energy, cold dark matter models of our universe and combine it with the Planck data, all these other techniques using the early universe, they give us a value of like 68-ish. 68, 74, not the same number.
And you know, for people who had been following this, the overlap was, you know, there were error bars, but the error bars kind of did this, right?
Yeah.
Really close.
Now they're like this.
Right. And so now, thanks.
So now they're each more accurate or more precise, but further apart.
Right. So they're kind of like this. And now
there's what's called a 4.4 sigma difference between these results. And they put the possibility of this being an actual error at basically so low a probability that it is not an actual error. Now, there's all sorts of different ways to explain what we're seeing. It could be simply that neutrinos are interacting with one another in ways that we don't know. It could be that dark energy actually varies with time. It could be that dark matter early in the universe interacted. What it tells us is some of this stuff that we don't perfectly understand could be doing really cool things that is evolving our universe in ways that we hadn't thought of. And the universe, once again, is more creative than we are. And we just need to catch up.
And even like a couple of months ago, there had been a survey that had been done using quasars as a method of a standard candle, and they were able to see like even like about 1.5 billion years after the Big Bang, and they were starting to see that drift from the baryonic, you know, point to this 1.5 billion years after the Big Bang to the modern age. You can see this accelerating acceleration. So clearly something is in the card. So if of all of the possibilities, I mean, the one that is the most unsettling, and I don't know why, because you know it's all apocalypses in the far future, is this idea of the big rip, that in fact dark energy, the amount of dark energy is increasing and accelerating, and eventually we're going to get to a point where galaxies are pulled apart, and solar systems are pulled apart, and planets are pulled apart, and black holes are pulled apart about 18 billion years from now, maybe 70 billion years from now, you know, some amount once they measure it. How does that...
The probability that this is just like we don't fully understand particle physics, which we already know we don't fully understand particle physics, and this is simply a matter of interactions of particles are acting in a way that we still don't understand, that is consistent and not scary. One of the first theories when we first found dark energy back in 1998 was it was what's called vacuum energy. It's coming from this constant appearance and disappearance of virtual particles, and when they ran the math, they were off by a factor of 10 to the 140, so it didn't work. But we also didn't even know that neutrinos had mass until 20 years ago. So there's so much that we don't know. We don't know even what the particles that make up dark matter are. And it could be that 10 to the 144 goes away once we figure out what's going on with dark matter and all these other suites of particles we don't understand.
Larry Beckham asks, so we got the figures on the beginning, and now how can we get the intermediate values? Is that the key that we need, is to see it changing over time?
And see it changing over time will help us figure out, is this a constant change? Is this a non-constant change? Good Lord, that would be impossible to try and figure out. And the trick that we're running into, the trick the universe is playing on us, is we can measure the distances to type 1a supernova to fairly good distances, 1 billion light years away or so. But then there's this huge gap of universe where we can't see those type 1a supernovae. And it's not until we get to the 10 plus billion year, it's actually more than that, the 12 or 13 billion light years in the past, that we start to be able to figure things out using these other techniques. So we need to figure out how to use gamma ray bursts, how to use active galactic nuclei, how to use these things that we can see in all those intervening distances to measure the distances. And then we can start to figure out what's going on in the intervening universe.
And so that's going to be new tools, right? That's going to be the James Webbs and the W-FIRSTs and the LUVOIRs and so on to help us get, and all the ground-based observatories.
And just getting a better statistical understanding from the Large Synoptic Survey Telescope. If we can realize, there's this kind of galaxy that always behaves the same way, and now we've seen 20 of them instead of 2,
right?
Then we can figure this stuff out.
Arjun asks, how long until LIGO can help with something like this?
I don't know.
I guess you would need...
We haven't figured out really how to get distances from gravity waves yet.
You would need a standard candle, but in gravity waves.
Yeah.
And then somehow be able to, use the same techniques. And right now we're just at the we can detect them at all phase.
Well, and it doesn't necessarily have to be something like that. One of the coolest ways that we have for measuring distances is by looking at variable sources that are lensed and measuring the difference in a variation occurring in different members of the lensed group. Each of these things will have traveled a different distance, and by working out, okay, so this one traveled this distance, this one traveled this distance, this is the light delay time in the variation, we can actually measure distances. So there's all sorts of cool ways using geometry and other stuff, but it's trickstery.
Right. And so, you mentioned maybe it's dark matter behaving, we don't even know what it is, but maybe dark matter is a thing, and maybe... Do these give us clues on some of the paths to go down to try and understand some of this other stuff that we don't even know what it is, right?
Yeah, there's a whole suite of different things that need to be explored. And right up at the top is looking at the dark matter particles, looking at neutrinos, and just trying to figure out what's going on with these things that, well, we can't always detect in laboratories doing what we want them to do. It could be even that there's kinds of neutrinos that we hadn't previously theorized. It's going to be a cool new period. And what I'm going to be interested to see is, does Adam Rees get a second Nobel Prize for being the observer that figured this out?
Right.
No, we'll give it to someone else.
Yeah.
Well, there's going to be a theorist involved. We need a theorist somewhere to explain this.
But Fraser, speaking of LIGO helping us out doing stuff, what is LIGO up to?
Oh, I'm glad you asked. That's like the first time anyone's ever set me up for a story. This is great.
There you go.
It's very civilized of you, Kimberly. Yeah, so we talked about this a month ago about how LIGO, the new version, the '03 edition of LIGO and Virgo are back online, and both have received tremendous upgrades. And we talked quite a bit in detail. I think Morgan talked about what was going on with LIGO. They have doubled the power of the laser. They have swapped out 5 of the mirrors so that they're a lot more mirrory. They have also used a bunch of really clever techniques with this thing that's called quantum squeezing. And what they do is essentially they are, with quantum mechanics, you've got, the uncertainty principle. You can know the amplitude of the photons that are coming in, or with great accuracy, or you can know the strength, and so they are able to the position or the amplitude, and they are able to essentially make the amplitude less statistically relevant and able to then amplify the position, and that allows them to detect the signals of the laser beams out of the quantum background fluctuation, which is quite amazing. It's this technique that was used. The Australians pioneered it, and they were able to attach it, use this methodology into LIGO and Virgo. And then the other thing is Virgo actually received, that's the European ones. You got the LIGO, which are the 2 observatories in the US. Virgo is the one that is in Europe, and they were able to greatly enhance Virgo's capabilities, being able to push its detection. And that's really key because now you've got this 3-dimensional view of the sky. You've got the 2 LIGOs in the US, and then you got the Virgo Observatory. And with those 3, you can triangulate the position of any of these gamma ray bursts, any of these gravitational waves that are happening as they pass through. They pass through the Virgo first, and then one of the LIGO observatories, and then the other, and that tells you where it came from. Before that, we could really only know them to within the hemisphere of the sky. And the last big thing is that they're going to be fully operational 24 hours a day, 7 days a week, pumping their observations directly out onto the internet. And what they've been doing is they've just been blasting it out. So as soon as they get a candidate discovery, something of interest passes the detectors, the computers immediately tweet out the observation and give observational astronomers the information they need to be able to do their follow-up observations. And then the folks from the LIGO Virgo teams will analyze the results and either confirm it or retract it and go, nope, that was a mistake. We didn't mean to do it. So you can actually get all of these live discoveries on your smartphone. There's an app you can get where your phone will beep every time they discover a gravitational wave. And with the enhanced capability of it, there are the black hole mergers, which they were expecting to see, more of the neutron star mergers, and hopefully they're going to be able to detect black holes eating neutron stars, which has never been seen before. And the other thing they're going to look for is neutron stars that are rotating off axis and kind of providing a wobble that should be detectable. So we are now a month into the observing run, and LIGO actually just posted this today. I'm going to put this up here. I'll let my co-host be able to see this as well. So these are all of the potential observations that have been seen so far. So on the 8th, 12th, 21st, they saw merging black holes, they think. On the 25th, they think they saw another kilonova. So they saw 2 neutron stars colliding into each other. And on the 26th, they think they saw, so 4 days ago, they think they saw a black hole eat a neutron star. And this is all totally
so
fresh.
Cool.
Yeah. And so again, they are just like, if you look at the feed, they are just absolutely dumping data like crazy out onto the internet. So here we are, 4 weeks into the new observing run, 5 observations made so far, right on schedule, a little ahead of schedule, 1 observation a week. And again, up until this point, the combined might of LIGO and Virgo had discovered 10 total events, 9 black hole mergers and 1 kilonova event. Here we are, 1 month in, 5 results already, including this one that they had only speculated on, maybe. And so the problem is that it's also fresh, it's also new, and it's all happening in real time. That there's going to be there's already been a couple of retractions over the course of this month. So totally
So I
stoked.
mean, I think the fact that they're announcing everything right away and getting it out there into public so that people can look at it is actually it reminds me a lot of what the Kepler mission did, in that they would always announce Kepler objects of interest, and now TESS is doing TESS objects of interest, which are just things that seem like they may have a signal that we might want to look at, but aren't necessarily the thing we were hoping to see. And so maybe this is a whole, I don't know, I'm not good at making up new acronyms. Gravitational wave object of interest.
Yeah.
Void. That's weird. don't use that.
No, we'll give you another couple of weeks to come up with a new one.
But I have some time. I'll figure something out.
All right.
But I think what this means is that if you have a backyard telescope that could potentially see some of these objects, what you should do is sign up for these alerts and then just camp out in your backyard and go look for the visual remnants of black hole mergers and black holes eating neutron stars, which, can I say, how cool is that?
Yeah. Like
black
three
holes
of them,
eating neutron stars.
The black hole mergers, they would be invisible. No amount of your sitting in the backyard with your telescopes would let you see it. But neutron star collisions with a pretty good, I think they can go out to about 650 million light years is the distance. Right now they can detect them, and so they can detect them. That's absolutely, the flash of that is detectable by a person's backyard telescope. I mean, we could see supernovae out beyond that kind of distance. So I think you're exactly right. And then of course that amazing black hole eating a neutron star, they're going to need as much data as they can possibly get as quickly as they can get it. So I think you're exactly right.
So, I mean, it seems to me like now that things have started up again, they're going a lot faster. The discoveries are coming a lot sooner. How long do you think it'll be before we have enough to be able to do some population statistics on some of these events?
Man, I don't know. I mean, I think the whole point of this really is it's this live updating that was the shift, really the big shift this time around, as opposed to making their detection quietly, telling astronomers, taking 2 months, writing a big paper, all in secret. This time, everything's happening, and the more of them that they get at various kinds of distances, we will start to learn more and more about how often these things are happening around the universe. But I think it's still so early.
I think the most important part is going to be getting those optical and other multi-messenger forms of follow-up, like happened August 2017 with the neutron star collision. When we have these abilities to combine data from multiple different kinds of detectors, it gives us so much more information. If we keep detecting things that no one's able to follow up on in the optical, no one's able to follow up on in particle physics, it's going to be a lot harder to build those population studies. So this is one of those times when luck is going to play a role. And part of the beauty of getting these detections put out live is we can go and start doing like we used to do with gamma ray bursts and have people walking around waiting to get that notification, except instead of beepers, it's now your smartphone. Get that notification that, hey, someone needs to slew over and check out this quadrant of the sky.
Yeah, and that's the thing, is that it's still not super precise. I mean, they're able to provide you a general quadrant of where it's happening, but not the specific area. So there's still a bit of a hunt to it in actually participating in the search for it. And then, so it's really exciting. I love it, and I would love to see some of these. I would love if they could actually find this black hole eating a neutron star. I just love the idea of this sort of terrifying nightmare that would go on with that.
Why is that any more terrifying than a black hole or neutron star collision? It's all
because
the same
those neutron stars could have planets.
Right.
Well, so could the black hole. They're just probably less likely to be occupied.
They're all not likely to be occupied.
But we know that neutron stars can have planets because we found them.
Yeah, a neutron star is still made of
Yeah.
stuff we could still kind of barely understand, so we have a connection to it, while a black hole is just a mysterious...
Tugs at our heartstrings.
Yeah,
more.
exactly. Yeah, yeah. If we had to pick,
Black hole. That's just how
Eh.
this.
All right, Kimberly, we got like a couple of minutes left. Tell us about a weird thing on Titan.
Yeah. So this is a story that, hey, we saw a weird thing. We weren't expecting to. Solar radiation and radiation from Saturn and things like that's going to break apart the methane. The methane's going to be lost on a relatively quick time scale in the scheme of the universe, unless something from the surface or beneath the surface replenishes the methane in the atmosphere. So astronomers went looking for that kind of mechanism. Maybe it was cryovolcanism or some sort of other eruptive process, or that brings fresh methane from underneath to the surface that then makes it to the atmosphere. But instead, what they found was a very strong stripe of methane ice that goes around about 40% of the circumference of the moon. Just a little narrow little stripe of methane ice, rich in organic materials. And we're not expecting to find it. They don't know why it's there. It's not associated with any particular geologic feature or other known phenomena going on Titan's surface. They don't know if it's at all related to replenishing the methane in the atmosphere. But Titan just seems to have a stripe of methane ice spanning most of its surface. Or most of its circumference. So that's weird.
Yeah.
And we don't know why.
And you
or what it
you
does.
would expect to find that at the poles where it's coldest, right?
Right, and it's not at the poles.
No.
It sort of goes across it goes across the equator a bit. It doesn't reach the poles on either end, as far as they can tell. It's not on top of a ridge. It's not at the bottom of a valley. It's not, scored up from the surface. They don't know if it's, upwelling from underneath or being deposited from above, or if it's trickling down somehow and then getting spread out into a stripe. They have no idea. It's essentially saying, here it is. This is strange. There's
And
methane
awesome.
ice. And awesome.
Awesome.
It's one of those, we keep looking at Titan and we look at it more and more closely using different analysis techniques on the same Cassini and Huygens data like they did here. And as we get better at analyzing the data and coming up with new creative ways of looking at it, because we're not going back there anytime soon, we keep finding really weird stuff going on Titan.
We've got to go back.
We've got to go back.
Yeah, that's it. It's decided. With this,
Yep.
with this methane ice belts.
Tiger stripe?
Belts, yeah. We've got to go
Belts?
back.
Belt.
Something.
All right, Kimberly, it's time to bring the show to a close. Oh, you were on my screen, but now Pamela's on my screen. So Pamela's going to get a chance to let us know something interesting that she's worked on. Pamela.
I have been painting planets and trying to figure out how to recreate the thermodynamic effects of gas using various densities of paint instead. And I encourage all of you to go see just what is possible with acrylic paint on acrylic discs at 739studios.com. And the next thing that is up is we're going to be mixing salts in to see if we can recreate all of the chaotic terrain.
Oh, that's cool. Like actually have some like physical features
Have
on
the
your
crystalline
planets.
structures forming in the paint.
Oh, that's really neat. Very cool. Kimberly.
So I've been working on a couple of awesome articles for EOS. The first one I talked about tonight was the discovery of water in these Itokawa grains, which is super cool. So that article's up on eos.org. I'm also working on something about a really cool art showcase done by the Psyche mission that features a lot of awesome creative works from undergraduates being inspired by the mysterious metallic Psyche asteroid. So that should be up online soon. And you can check out all those really cool images at the Psyche mission website as well. And something about how the ocean has a lot more viruses than we ever
I
expected.
saw that. Yeah.
Yeah.
Never
It's
swim
not-
again.
it's not something I ever thought I'd be writing about. But man, is ocean water filled with viruses.
That's awesome. So if I seemed somewhat knowledgeable about LIGO and Virgo, that's because that's what my new video was this week. So go definitely and check out my channel. I also had a delightful conversation with Jeff Notkin, Meteorite Man, and the new president of the National Space Society, and that was on Monday on my open space. So if you want to see us nerd out about asteroid mining for an hour, definitely check that out. And then the new episode that just came out. All right, let's put you all back together again. There's all of us. There we go. Huge thank you, of course, to our special guest, all of the people watching this show today, all of the great members of the Weekly Space Hangout crew. We really couldn't do this without you. Thanks to the moderators, and of course, my co-hosts who are here today. Thank you. For continuing to make the space happen. We all appreciate it. We will see you all next week. And I know it's going to get cut off at some point, so I'm just going to talk, and then there's going to be some weird ending. So